Hello, in this video I'm going to show you how to mess with people using lookup tables and also go into some historical topics which I hope you'll find interesting. So we're going to talk about this guy, Jordan Mechner. He's the author, architect, brain behind the Prince of Persia franchise, but that was not his first game. Before he did Prince of Persia, he was known for this game, Karateka or Karateka. I think the former is the correct pronunciation. And when you started it up, you'd see this dojo on the left here, and the screen on the right shows some gameplay, although that looks like it might be from a more modern system based on the resolution. And what platform was this designed to run on? The venerable Apple II. So Karateka designed to run on the Apple II. So let's talk about what it took to get images onto the Apple II screen. Also notice the disk drives here. They're going to factor into our story later. But before we get to the disk drives, we're going to talk about graphics, how to get graphics onto the screen. So there were several video modes. There was a text mode, a high-res mode, and a double high-res mode, which is not used very much. And there were two 8K chunks of RAM that were dedicated to storing the picture that the hardware would display. So if you have 192 by 280, that will fit into an 8K chunk of RAM. So there are two 8K chunks of RAM dedicated to storing the picture on the screen. Why two chunks of RAM? Well, because when you draw a picture onto the screen, the stuff that you draw first is on the screen longer, and then as the hardware refreshes, you will see the stuff that you draw later kind of gradually show up, and then the stuff that you drew last is on the screen for less time than the stuff you draw first, and you end up with this problem of, it's called flickering and tearing, that the image looks like it's flickering. And so the trick is to have one picture be displaying while you're building the second picture. And when the second picture is ready, then you flip which chunk of RAM the hardware is displaying. So while you're displaying one picture, you're building a second picture. That's called double buffering or page flipping. And in Windows Forms, if you scroll down into the through the properties on a form, you'll see there's actually a checkbox for double buffering, which is exactly what this is talking about. It's the same thing. So there's a dedicated chunks of RAM for copying data that would be shown on the screen. Now, somewhat perplexingly, although this was not uncommon, the video memory is interleaved. Like, what is that? What does the interleaved mean? It means that, like, the first or the second line of the screen does not follow the first line of the screen in memory, and the third line of the screen does not follow the second. So the lines are grouped into, like, the first. The second lines of the first 8 chunks of the video. It's kind of they're grouped into some scheme, which means that you can't just kind of blindly copy stuff to the screen and think that you're going to get the result that you expect. And I'll show this in a second. But you just all you have to understand about interweaving is that the RAM in memory is not sequential. So if you copy stuff into the screen, it will not show up sequentially on the television or on the monitor. So that's what interleaving means. The video memory is non-sequential. So this makes it very hard to draw stuff, because when we draw stuff, we want to copy a line of pixels, drop down a line, copy a line of pixels, drop down a line, copy a line of pixels. Well, you can't do that easily if when the RAM you're copying into has this interleaved format. You can't just copy stuff sequentially into memory and expect that it will end up sequentially, like row after row, on the screen. And the whole purpose of this was just to reduce cost. The legend has it that Steve Wozniak was able to save 2 chips and out of the final design, and also reduce the complexity of the circuitry, the tracing, connecting all the chips. So it was done to reduce complexity, and Apple II was not the only platform to do this. But it's that interweaved video format that we have to work around, and that's where the lookup tables come in. So if you look at Apple's documentation, they show that the screen is laid out like this. I mean, you look at that grid, that's a two-dimensional array. And it is broken up into boxes. So each one of these little things is kind of called a box, and it represents an area of memory that is 1 byte wide and 8 bytes tall. So maybe think of something like a character. It's 1 line of pixels wide and it's 8 lines of pixels tall, kind of like this cursor character over here. And there's blank pixels on the top and bottom and left and right. So you have to take those into account. So if you wanted to copy this screen into the memory, you'd have to say, okay, well, I want to where do I copy the first line? Where do I copy the second line? Where do I copy the third line? Where do I copy the fourth line? Until you copied all 8 lines. And you can't just copy them sequentially into the memory because the memory is not sequential. It's interleaved. That's what these numbers here on either side of this diagram are for. They are lookup tables. They are here to tell you how to find the byte in memory, the location in memory for any y coordinate. You say, okay, well, my y is 10. Which memory address, where in memory is that? Where does line 10 start in the video memory? That's what these tables are for. They're lookup tables. There's a lookup table right here. There's a lookup table right here. The numbers with the dollar signs, these are in base 16, and these are their equivalents in base 10. So that's why there are 2 sets of numbers here. So let's talk about the process. Let's say I've got a sprite and its y coordinate is 10. How do I find out where in memory line 10 is? Well, we need to understand the documentation. So our screen is divided up into boxes, and we have to figure out which one of these boxes our line is in, and we have to figure out which line within the box that is. So imagine we wanted to copy, like we got something that's y is 10. 10 divided by 8 is 8 goes in once, so that's in box 1. Just as the boxes start at 0, so it's box 1. And 10 modulus 8 is a remainder of 2, so that's line 2, box 2. So so that's what we have to do. We have to figure out what box is our y coordinate in, and then what line within that box is it. And then we can use those values to look up memory addresses, a memory address and an offset. We add them together, we get our final value. So again, to locate the memory address for a y coordinate, you have to figure out what box it's in. To do that, divide it by 8. That'll tell you which one of those boxes you're in, and you start with that number. You grab that number and you write it down somewhere, or store it in a variable. So if so any of the first 8 lines of screen will have their starting offset as 8192. Any second lines of the next lines of the screen, the next 8 lines will have their initial offset to be 8320. So we just divide y by 8 and use that to pick one of these values. Right? Think of these as values in an array. This is a whole line of values. This is an array. All right, so once we've figured out what box it's in, we look up our number, and then we have to figure out what's the offset for that line. And again, you could think there's an array of values right here, 0, 10, 24. We're going up by 10, 24 every time. So figure out what line it's in, and then add the corresponding value to our initial offset, or to our initial address. So, and then that gets us our final value. So, compute the box number, look up the memory address for that box number. Then we look up the line number to get an offset. We add this offset to our box number's address, and then that tells us where in memory that the line of pixels for that y value starts. And then to get the column, we just add our x value to it. So maybe our x is 21 or something bytes over. Then we just add 21 to the address that we computed, and now we've jumped 21 bytes over. Now we know where to copy that line of pixels onto the screen. So it's a double lookup. It's like, okay, we know what our box is. Look up the starting address for the lines of that box. We'll figure out what line it is. use that to look up the offset. Add that to the first thing that you looked up. Now you know where that line starts. Then add the x value to that to get the column, and now you know where in memory you can start copying your data. So again, look up the offset for the box, look up the offset for the line within the box, add those two together, add x. Now you have the memory address to copy that line of pixels into. So 2 lookup tables just to figure out the y coordinate of where in memory is associated with something's y coordinate. That's kind of clunky, but again, it was to keep costs down and with the idea that the programmers will just have to deal with it. So we could speed this up though. Remember, our screen is 192 pixels tall. We could build an array table of 192 values and pre-compute the y values or the offsets for each one of those y values. That's a smart thing to do. All of these calculations don't necessarily have to be done at runtime. So imagine you've got something on the screen that has a coordinate and it's not moving, right? Why compute the math? Why do the math every cycle, every game refresh to figure out where to draw that thing? Just look it up in a table and do the math once at initialization time when you build the table or design the table and hard code the table into the program. And now you don't have to do that math anymore. You don't have to do that math every game update. You've already done it. Just, okay, my y coordinate is this, look up the offset in the table. And that's what the game actually does. So it builds a lookup table for the y offsets to speed up the drawing. But Jordan Mechner thought it'd be very funny that if on the B side of the disk, they copied, they had an identical copy of the program, except that the values in the table were inverted. Now, this means that they actually have to go through the hassle of putting copying a second side onto the disk as opposed to just having it blank. It's more time consuming, more labor, and more wear and tear on the machines. But Broderbund, to their credit, said, yeah, this is a good idea. We should go do it. Why? Like, what's the payoff for putting a B side on the disk with a table where the values are flipped? And the answer is, when you put the disk in, you get this on the screen. If you put the disk in upside down, the game is upside down, and it messes with people's heads, and they think, well, maybe that's how disks work. Like, if maybe bits have an up or down or something. I don't know. It was just a funny idea, and I'm glad they did it. But Jordan Mechner said that, to his knowledge, no one ever returned a disk being faulty. It sounds like not too many people ever made the mistake of putting the disk in upside down, and those that did probably quickly figured out their mistake and realized that it was all a joke. So there's some fun with lookup tables, right? Rather, all they had to do to get the game upside down was just take that lookup table and change the values in it. So when you tried to draw stuff to the screen, it would end up at a different y coordinate on the screen. Every y coordinate would map to a different address in the computer's memory. And the result would be that the game would be drawn upside down. So there you go. If you're interested in learning more about either of these two games or franchises, Jordan Mechner has published memoirs on both. I've not read The Prince of Persia. I've read some of Karateka. He was a student at Yale, and I grew up in New Haven, and he talks about locations that like Cutler's Records that are no longer there, but I remember them being there growing up. So if you've ever toured Yale and you've or have lived in New Haven, you might want to read the memoirs just for that. It's just kind of neat to realize what else was going on at that time. So there you go, fun with lookup tables, how to mess with people using lookup tables, and some history in there as well. And if you actually want to play Karateka, you can now get that on your phone as an iOS app. It is not gone away. It's still out there and enjoyable to play. So hopefully, having seen this presentation and realizing how hard it is to get graphics onto the screen of any of these old systems, maybe you'll appreciate all the hard work that went into them just a little bit more.